Hello and welcome to this EE328 lecture video on discrete time system analysis. In this video we're going to treat discrete time systems as difference equations and solve those using the zero input response and zero state response decomposition, much like we did in continuous time. So let's get started. So in addition to solution by recursion, one can analyze the output of a system using the ZSR and ZIR decomposition method. So again, ZSR is a zero state response and a ZIR is a zero input response. Just a quick warning, there are some resources out there, including I think some prominent Wikipedia articles, that will tell you that the zero input response is the same as the natural response and the zero state response is the same as the forced response. And if you adopt that notion, then you can solve these systems using similar methods. But I am going to reject that and treat the ZSR and the ZIR as different things than the forced and natural response. The motivation for doing this is that if you make this choice, then the outputs you observe, i.e. the ZSR and the ZIR, are actually the physical outputs that you would see from a system, whereas the forced and natural responses together, they will give you the same total response, but they do not necessarily decompose into the output when there is no input and the output when there is no initial state. That sounds a little more complicated than I wanted it to be, but long story short, we're going to treat the ZSR and ZIR as different things than the forced and natural response. Okay, so let's get into the anatomy of a difference equation. So on the left-hand side, we have terms involving the output. And this, just like in continuous time, is called the homogeneous part of the equation. That is, if you set the left-hand side equal to 0, you get the homogeneous difference equation. The right-hand side contains only terms with x in them. This is known as the forcing function, or sometimes just the inputs. And again, you can have arbitrary capital N's and capital M's. When capital M equals 0, we have what's called the single input case. And that'll become relevant because our knowledge of superposition will allow us to generalize, solving just the m equals 1 case, and then allow us to use time invariance and linearity to solve for more general cases. And the other thing I want to point out is that we are going to refer to the order of a system by the number of delays on the output. So this is a capital Nth order system. Now the last piece of the puzzle are these initial conditions, which are slightly different than what they look like in continuous time. That is, they are values that the output takes at times before 0, or times before the input is applied. Now we saw these pop up kind of naturally in the solution by recursion because to get the output at y of 0, you often need earlier outputs, right? Especially, if the system is recursive, by definition you need earlier outputs. So we incorporate that into what are called initial conditions here. If you want to call them pre-initial conditions, that might help you keep them straight if you're dealing with both discrete and continuous time. But for our class, which is exclusively discrete time, I'm just going to call them the initial conditions. Another way to think about them, and to justify why you would need the value of the output at times before 0, is because they represent the history of the system. Right? And some systems have memory, and so the output at any given time can depend on past states of the system. And we're going to represent those past states of the system with the outputs at past times. A final way you can think about this is that if you think about the output as, or the system in that block diagram formulation, these are like initial values in a shift register. So yeah, if you pick up a digital system, there's no guarantee that the shift registers inside that system are all 0. Perhaps you have initial values in that shift register, and so you would need to exhaust those values in order to get the output due to new inputs. Okay. So we're going to write the total response to the system, or the total output, as the sum of the ZIR and the ZSR. So the ZIR is a little simpler, so we're going to treat it first. It's a little simpler because of this property. It only contains characteristic modes. What's a characteristic mode, you might ask? Well, let's solve the homogeneous equation, right? That means we're setting the left-hand side equal to 0. And the solution can be found by seeing that this is the sum of weighted and shifted functions. And that sum has to add up to 0. And the only kind of function that has this property, that if you weight it and time shift it in discrete time, are functions of this form. So constants times constants raised to the n. So it's only these kinds of functions, where different c's and different r's, can satisfy this. Now I'm going to have to modify that in a moment because of things like repeated roots and all that. But for the time being, let's see why that might be true. So we're basically going to try this. And the only knowledge we have is that this function y of n has to satisfy the homogeneous equation. So if you plug it in, here's our y of n, here's y of n minus 1, and here's y of n minus big N. Now, these terms all have a lot in common. In fact, they have the c in common. And if we factor out a little r to the little n, then what's left is the constants a and a bunch of r's raised to negative powers. Now, alternatively, I list these two on the same line because you can choose one of two paths, and you actually get to the same answer. If instead you factor out this quantity, r to the little n minus big N, then you're left with the a's in the same order, but now with r's to positive powers. And in my book, it's easier to think about polynomials with positive powers. However, it is kind of neat that the roots of these two polynomials, so the roots of this polynomial and the roots of this polynomial, are the same. You will both, in both cases, you will get n roots, which I'm going to call little r sub 1, little r sub 2, all the way up to little r sub n. And just as a heads up, these can possibly be complex, just like they could in continuous time. So what this means is that all capital N of these roots work in this equation, which means that linear combinations of them will work as well. So I'm allowing for different scaling factors, and these are what are called characteristic roots that we're plugging in here. So finally, I can answer the question of what a characteristic mode is, and it's simply this. It's a characteristic root raised to the n. Now, like I said, there is the assumption when I'm writing this that all of the roots in this list are distinct. They don't have to be, and if they are, then you're going to get a slightly different form of the characteristic mode. So let's break that down right here. There are 3 types of characteristic roots. Type 1 would be real and distinct, so not repeated. And in this case, you simply get exactly what I've listed here. R to the n is your characteristic mode. In the second type, you have possibly repeated, either real or complex. And however many times you see the root repeated is the number of times you have to iterate this list. So r to the n r to the n squared r to the n, etc. So if you have a triply repeated root, then you would have three modes: r to the n r to the n, and n squared r to the n. Just a doubly repeated root would mean just the first two in those lists, etc. And lastly, the kind of tricky ones are complex and distinct. So in this case, and whenever you have real coefficients, so if the a's are real, you will have an extra property that there will always be a complex conjugate pair to any complex root. So if I know R1 is complex, then I know there must be another root. I'm going to call it R2 that is R1's conjugate. Another thing that has to hold true is that the coefficient on the root number 2 has to be the complex conjugate of the coefficient on root number 1. Now these two things taken together mean that the modes that this pair of roots contribute to looks like twice times the magnitude of the coefficient times the magnitude of the root, and magnitude here I mean in the complex sense, times the cosine of n times the complex phase angle of root 1 plus, so it's a phase shift, the complex phase angle of the coefficient C1. So this is the characteristic modes corresponding to complex R1 and R2. And I say it's a plural set of modes because one can think of this as the sum of an unshifted cosine and an unshifted sine, simply because of the phase shift here in the cosine. So we count that as two different modes. Okay, and so then when you add up all of these scaled characteristic modes, you get what we call the homogeneous solution. Let's see an example of how this would work. So given a difference equation listed here and an initial condition listed here, let's solve for the ZIR. Now first things first, if the input is 0, then the x's have to be 0, and so that's why it boils down to the homogeneous case. So again, we're going to try y of n is some constant times a constant to the n, and if that's true, if I plug that into the homogeneous solution equation here, I get c times r to the n plus 1/2 c times r, what is it shifted, n minus 1, that has to be 0. Now I can factor out a c r to the n minus 1, and I get 1 times r plus 1/2 equals 0. And yes, I hear you saying that r equals 0 is a possible solution to this. In fact, there are n minus 1 r's equal to 0. But remember what would happen. So if we count r equals 0 as a valid solution, what does that mean? That means that our homogeneous response is going to be c times 0 to the n, which is 0. Okay, so that's my quick aside to say why we don't count these roots, because they contribute literally nothing. So the characteristic root here is negative 1/2, which means that our important homogeneous response is going to be some constant times r1 to the n, and we now know that that looks like some constant times negative 1/2 to the n. So how do we figure out the constant? That is where the initial condition comes in. So the ZIR as a function of n is going to have the homogeneous form, so it's going to look like c1 minus 1/2 to the n. But we know something about the ZIR that we didn't particularly know about the homogeneous, and that is at n equals negative 1, the ZIR takes the value of 2. Okay, so on the right-hand side, I simply plug in n equals negative 1, and I solve that c has to be negative 1. At the end of the day, the ZIR as a function of n is negative 1 times negative 1/2 to the n. Now, this does work for n equals negative 1. We just showed that it works, but generally you're talking about ZIRs as being from n equals 0 onwards. Now, I just want to quickly point out that I foresee this being an issue. That I just want to say that negative 1 times negative 1/2 to the n is not the same as 1/2 to the n. Okay, so note. The ZSR, or zero state response, contains both characteristic modes and forced modes. So remember, characteristic modes come from the characteristic roots. Forced modes come from the forcing function. And so the Amberdar book has this really nice table of, if you give me the forcing function form, then I just have to look into this to find the form of the forced response. And another name for this column would be forced mode. If the forcing function is a constant, then the forced mode is another constant. If the forcing function is phase-shifted cosine, then the forced modes are either the sum of a unshifted sine and cosine, or a different cosine with a different phase shift. Okay, so this mirrors what you learned in continuous time differential equations. And the reason, I think it's nice to point this out again, is that the reason that we have to consider characteristic modes in the ZSR is because we know that anything that YH of n, anything that belonged to the homogeneous solution, is such that if I plug it into here, I get 0. Okay, so if I, in addition to that, have the forced solution, which when I plug it into here, I get x of n, then if I were to add these two, I would add those two, and then I wouldn't change x of n, so I would make this statement true again. Okay, so we have to include both forced modes, clearly, and characteristic modes. Let's see an example of this. So we have the system with the same homogeneous part as before, and now we're forcing it with just x of n, and I'm going to let x of n be the step. So we're looking for the step response of this system. So in the table, we see that this looks like a constant for positive time. So that means that the shape, or the mode of the forced response, is going to be a constant. So what constant? It's a constant that when I plug it into the inhomogeneous CFEQ, y forced of n plus 1/2 y forced of n minus 1, I get u of n. Now the trick here, to go from this line to the next, is pick a large n and make it work, basically. So I have k plus 1/2, well, this is a delayed version of the force function, but if I pick a large enough n, then the step will have turned on and I get k again. And if I pick a large enough n on the right, I get 1. So this allows me to solve for the forced mode is just 2/3 constant. So in addition to the forced mode, we need the correct amount of homogeneous response. So the ZSR here is going to be the sum of the forced mode that we just found with some amount of characteristic mode. Okay, so this is 2/3, and the homogeneous response has the same form as the previous slide, but with a possibly different scaling factor, c. How do we solve for this c? Well, we know that we're solving for a zero state response. And so this is, in this case, saying that the output at time -1 must be 0. So we again take this at n equals -1. We know the left-hand side has to be 0 at -1, and the right-hand side looks like a constant plus a constant times -1/2 to the -1. Okay, so if you solve this, you get c is equal to 1/3, and so the zero state response is the sum of 2/3 and 1/3 minus 1/2 to the n. Now there are two ways that I could finish this. One would be, say, comma, n greater than or equal to 0, because the response to a step, and the step starts at n equals 0, can't preclude or predate the step time. So this response, because we have a causal system, has to start no earlier than when the input started. So that's the argument for this. And if you buy that argument, then I think a more helpful way, especially when we get to the next slide, will be to think of this function being multiplied by its own little unit step. Okay, so this has the effect of clipping at n at 0 and above only, multiplying the rest of what's in the brackets by 0 for negative times. Okay, so once you have the ZSR for what I will remind you is the single input case, if you have multiple inputs, then you get to use superposition to find the ZSR in that case. I've included a couple of curveballs here. I have scaled the step, and I've also included a shifted version of the input here as well. Now remember, if we're doing the ZSR, we ignore non-zero initial conditions. Okay, so ZSR means that we get to ignore this. From previous slide, we solved that the single input case, the ZSR, was 2/3 plus 1/3 times negative 1/2 to the n. All of that times u of n. Now I call it y sub 0, even though I call it the single input case, because this corresponds to capital M equals 0 in the very first slide. I also know that this represents a linear time invariant system. I know it's linear because we're only doing linear things to these functions, scaling them and adding them. And I know it's time invariant because none of the coefficients vary with time. Okay, so those two observations mean that this difference equation maps to a linear time invariant system. And the benefit of viewing it that way is that if I scale an input, then I get to scale the output. Additionally, if I add a shifted input, LTI-ness allows me to add the corresponding shifted output. Okay, so we have a scaled input there, and we have a shifted input there. So that means that the ZSR of this system is going to be triple the ZSR from the previous slide plus triple the ZSR from the previous slide delayed by 1. Okay, so if you plot that all out, you get 2 plus the characteristic mode. That starts at time equals 0, and then we get a shifted version of that. And this is the utility of including this unit step on the end, is because I get to simply remember that when I'm shifting the single input ZSR, all I do is replace every n with n minus 1. Okay, in my book that's a little simpler to remember than making sure after the fact I get the right delay everywhere I need. So far we haven't really looked at the graphs of many of these things in the time domain. I think it's kind of instructive to work out what this looks like if I plotted it versus n. So I'm just going to look at this function now. It starts at n equals 0, so I have nothing back here. And at n equals 0, I get 2 plus a number to the 0. And that is always 1, so this guy starts up here at 3. And at time equals 1, it becomes 2 minus a half, so then 1.5. And then it bounces back up, and then it bounces back down, and then it kind of settles out. Well, it doesn't kind of settle out, it does settle out at 2. And that's because this term goes to 0 as n gets large. Right? It's a fraction that I'm raising to a larger and larger power. Now it's a negative fraction, so it's bouncing on its way there, but it does converge to 0. How about this one? So we're multiplying by a step shifted to the right, so I get 0, 0, and then 0. And now time equals 1 is where the old origin was. So now I'm just going to copy my old graph, 3, and then 1.5, and then it bounces back up, and it bounces back down, bounces back up, and this one also settles at 2. And you can see that because we are, again, taking a fraction and raising it to larger and larger powers. Okay. So both of these terms go to 2 as n goes to infinity. Now, I want to take a quick aside here, so we're doing a little bit of looking into the future, and I want you to compare these statements, like what functions in discrete time go to 0 versus what functions in continuous time went to 0. In continuous time, it was always things like e to the lambda t, and this goes to 0 as t goes to infinity if lambda was negative. Okay, and so this gave rise that if we plotted, well, if the real part of lambda, so sorry, if the real part of lambda was negative, so if we plotted all possible lambdas on the complex plane, then if our lambda ended up on the left half plane, we concluded that the mode attached to that lambda converged to 0. Now, contrast that with the observation that I just made. If I have a number like z to the n, it will go to 0 as n goes to infinity if the magnitude of z is less than 1. Right? I said if it's a fraction, then if I raise a fraction to higher and higher powers, then I converge to 0. I might oscillate. I might go -1/2, +1/4, -1/8, and that kind of deal, but I'll go to 0. And conversely, if z is in magnitude larger than 1, I'll start growing. Right? 2 goes to 4, goes to 8, goes to 16. And so this is our first little mini preview that if we plot again on the complex plane, real versus imaginary, that the range of complex poles that are stable, if I can use that term, are now inside this unit circle. Okay, so that's a quick preview. We're going to pick that up a lot in the coming weeks, but I want you to give you that preview because we can see it here. Okay, so to finish this example, the total response would be the sum of the ZSR we just computed on this page and the ZIR that we had from earlier in lecture, because this initial condition was the same from earlier in lecture. Okay, so if we plug in our numbers, we get the ZIR, which was -1 times -1/2 to the n, and that was valid for n's greater than or equal to 0, plus 2 and -1/2 to the n, starting at time equals 0, and 2 plus -1/2 to the n minus 1, starting at n minus 1. Sorry, starting at 1. And then there's a quick little cancellation that we can do. And that's because this is the opposite of this. And so that and that actually end up canceling in this particular example. That's not going to hold in general, but just in this particular example, we can simplify our answer. So this thing is going to end up being 2 times a unit step plus this delayed signal, 2 plus an oscillating, declining sequence. Last but not least, it's always nice to introduce a little bit of MATLAB into here. So in truth, what we just solved holds for all n, but if you're going to plot it, we're going to need to pick a finite range of n's. I just picked from 0 to 9. And then I defined our 0 input response as, like we said, -1 times -1/2 to the n. And recall that because we're taking a scalar and raising it to an array power, what we actually want is an element-wise exponentiation. Okay, and same story with the ZSR. So I did the ZSR in the unshifted case. So this is unshifted, but scaled. And this is the shifted by 1 case. And the way that I accomplish that is I, of course, raised to the n minus 1 power. But then I also did a Boolean test here. So this is a Boolean array. And for this particular example, it'll give me false, true, 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 on up to the end. Okay, so I'm checking which n's are bigger than or equal to 1. Well, the first one is not, but the rest are true. And so what I'm doing is I'm doing element-wise multiplication of this array times this array, and what that does is it has the effect of nulling out the first element and passing the rest of the elements perfectly through. So then the total ZSR, sorry for the mixed nomenclature here, I'm saying the ZSR is the sum of the unshifted ZSR with the shifted ZSR, and I can compose that with the ZIR and plot it over here. So here is our n equals 0, and what we get is this transient regime. So from about here backwards, we're seeing the transient response, and from about here forwards, we're looking pretty steady state. Okay, thanks so much for listening. I will see you in class.